Hi and welcome to MSc. In this video, we're going to be looking at optimizing geometric properties using a graphic display calculator. So here is a sample problem, and we're going to try to determine the dimensions of this storage box. It has no lid, and it has a total volume of 40 liters. Also, it has another constraint that the length is going to be equal to twice its height, and we're trying to minimize the surface area. So let's start by labeling some of the parts of this so that we can make sure we're on the right page in terms of what the different parts are referring to. So this is the height of the box here, the height of the bin. This will be the width, and then this down here will be the length. So we have some constraints that we need to work with. So let's talk about the constraints. And the constraints are things that are put on our problem that limit what our values can be. So one of them is that the volume has to equal 40 liters. And the other one involves the length and the height. And we know that the length is going to equal twice the height. In other words, we want it to be twice as long as it is tall. Okay? Furthermore, with the constraints, we also know that the volume of a rectangular prism like this is length times width times height. And now we can start to rule some of our constraints together, and we can look here and say, okay, well, the 40 liters, that's not going to be as helpful. Let's change that into centimeters cubed. And a centimeters cubed is the same as a milliliter, so we're going to multiply by 1,000. So this is going to be 40,000 centimeters cubed. And so what we know now here, instead of volume, I can write 40,000. And now instead of L, I can write 2H times W times H. And now, of course, I can multiply my H's together to get H squared. So 40,000 is 2H squared W. Okay, we want to take this one step further. We want to rearrange for one of these two variables. And that will fully integrate all our constraints into an expression here. And it's much easier to rearrange this just for W. If we rearrange for H, we'll have a square root, and that's just not going to be as nice to work with. So let's rearrange for W. And we do that by dividing both sides by 2H. So it's 40,000 over 2H. 40,000 divided by 2 is 20,000. So 20,000 over H squared. Right? Squared. Excellent. So that's our constraint work. Let's also take a look at our initial objective function. Initial objective. So initially, our objective is to minimize the surface area of this rectangular prism. So we know that the surface area is actually a function of length and width and height. Now you can see we've already eliminated, have a way of eliminating width, and we have a way of eliminating length in this equation. So typically what we have here, when we have this equation, is we have 2 times length times width, plus 2 times height times width, plus 2 times length times height. And that covers all 6 sides. But remember, this box doesn't have a lid, right? Again, we are working with it where it has no lid. And so we only, of the length times widths, we want the bottom part, but we have no top part. So really what we have here is this value here is gone. And this is the no lid piece. So we want to look for this type of stuff in the problems. If they wanted extra material, you could either change the multiplier or add an extra term on the end. And that would deal with extra material for flaps that cover up or overlap. Now what we can start doing is we can start implementing our constraints into this objective. And this is going to generate a revised objective function. So this is going to be building towards our revised objective function. Objective. Okay, so our revised objective is actually going to be just a function of h. It's the variable here that didn't get eliminated, and so we're going to put everything in terms of h. So instead of LW, L, we're going to put 2h. And instead of W, we're going to put 20,000 over h squared. 20,000 over h squared. Okay, so that's that first term. Then here we have 2, and h is fine, and the W again will be this, 20,000 over h squared. And then the last term here is 2, all right, times L, which is 2h, times h. And at this point, we could just enter this into our graphic display calculator, but let's clean this up and simplify properly. So as we work through this, we can see, well, the h here will cancel with the squared, and the 2 times the 20,000 will give me 40,000 over h. And if we look here on the next term, the exact same thing is going to happen again. So I'm actually going to end up with 2 of these, which of course I'll collect in my next line as well, over h. And then here we have 2 times 2 is 4, h times h is h squared. And let's put the squared term first, as is typical, and then because these have common denominators already, we can add the numerators. We're going to get 80,000 h. So this is our revised objective. It's a function of surface area, and its independent variable is the height. So this is what we'll enter into our graphing calculators. And we're going to try to find the minimum surface area, right? The question asked us to minimize the surface area. And there's lots of reasons we'd want to do this, some of which is just cost and efficiency, right? Using less material will have less cost, less product being used, and that's often what people designing packaging care about. So let's enter this into our graphing calculator. So here we go. We'll click on the y equals, and then we're going to enter our function, and our function was 4, and we used h, but we'll use x here. The graphing calculator doesn't care what letter you use. And there's the 4h squared, and then it's going to be 80,000 divided by x. So there's our function, and we'll click graph, and probably you'll get absolutely nothing most of the time with these types of problems. And again, this comes down to the window setting size itself. So let me show you some tricks on terms of what I suggest for window settings. We're not really worried about the negative. I'm going to leave it there, although we understand that negative dimensions here are silly. The x is the height of the box. This is what our variable is. And so we can choose a number for the x max. If I chose 100, that would be 100 centimeters would be the height of this thing. That would be a meter. That seems like a lot. So let's pick half that and say 50. Might not be that big. That might be way too big. But at least it gives us a starting point. Again, I'm going to kind of ignore the negative for the y min and just leave it like that. But the y max, this is where we need to kind of base it on something. And if we go back to our formula, the biggest number there I see is 80,000. So we could enter 80,000 there, and I think that's a fine choice. But we know that that's divided by h. So let's say that h is going to be at least 2. And let's say 40,000 here. Again, this is, oh, I think I did one too many. This is just placeholder values. You can play around with these more later, but sometimes students find it so hard to know what to even pick here. And that's my rationale for these numbers. So we're going to click graph, and there we can start to see part of the curve, and you can see the minimum. And so picking numbers based on the equation that you have is the best way forward with this. And of course, we're trying to find the minimum here. So to find the minimum, we're going to go second trace, which will unlock the calc feature, and we're going to go to minimum. And then it wants a left bound. So we'll cursor over, and we'll say, okay, there's a left bound, and we'll cursor over towards the right to provide a right bound, and then we're going to give it a reasonable guess. Somewhere in there looks pretty good, and we'll hit enter. And then it gave me my minimum. That's my height that will generate the minimum surface area, which is the other value written here. Okay. These values might change a little bit depending on your guess and your bounds, also the version of the calculator you're using and the algorithm that it uses to determine these points. So if you're off by a small decimal at the very end over here, that's not a big deal. It'd be a big deal if instead of 21.5, if you got 42, or if you got 0.08, right? These are big, big differences. But if you're getting 21.544 and some other decimal after that, you're probably just fine. Okay? If you're interested to know what this whole function looks like, you can play with the window settings and try to move things out to try to see what the whole function looks like. You can also try the zoom. If you try the zoom out feature and then hit enter, it'll zoom out and you can start to see the whole picture. Sometimes that's helpful to start to figure out where your function is, although sometimes I've found that zooming out can actually smush the part of the graph that you're interested in and can actually make it hard to see still. So just be a little bit careful with that feature. But we can see that we actually do have an asymptote here along the x equals 0, which is the 0 height, which makes sense because then it's not a box if it has 0 height. Its volume would be 0, and all sorts of problems would happen. So we do have an asymptote there. Okay? When we are trying to write this for an evaluation, obviously you can use your graphing calculator, but you can't import the picture right into your work. So my suggestion to students is always to produce a small sketch of the graph. Doesn't need to be super detailed, but just some type of indication of what the graph looked like. So that's what we'll do here. And we're really only interested in the first quadrant. You can probably get away with just drawing the first quadrant. I'll quickly sketch the whole thing here. The question didn't tell me what to sketch. So we had some type of system that's dropping off down here, and we had some type of, I almost refer to it as like a Nike swoosh here. Again, this is far from excellent penmanship on my part. Here's our minimum point. That's the point that we had. If we're recording the 3 decimal places, was 21.5, comma, and then it was 5,570, and that's both of these written to 3 sig figs. And that's my advice to you, would be to record to 3 sig figs. I know that's what programs like IB typically like, but you should always refer to whatever your teacher has set up as the standard for the class. What we have here now is we know that the height that's going to produce the minimum value is 21.5, and luckily I wrote that down while it was on the screen earlier, and I can write out the whole value here for you, 4.5, and that's going to be in centimeters. And we know the surface area that was produced as a result of that value. I'll put the ellipse there to indicate that it's an unrounded value. That will produce a surface area of 5,569.9066, and this would be centimeters squared. So we could even put an optimization statement here at this point, and we could say, therefore, the min surface area is, and this is where again I would round to 3 significant figures, and I would even say, let's use scientific notation this time, 5.57 times 10 to the 3 centimeters squared. Again, trailing zeros with no decimal are not significant. So this is 3 significant figures. This is also 3 significant figures. So the minimum surface area is that value when the height equals 21.5 centimeters. So there's my optimization statement, but that's really not what the question asked either, is it? It said determine the dimensions. So we have to determine the dimensions. Well, I figured out one of the dimensions right here. Figuring out the length, well, the length is just twice the height, so that's not bad. 2 times 21,544, ... Again, I advise personally not using rounded values. until the very end of the question. So that's why I have kept the ellipse there, indicating that it's an unrounded value. And when I do that, I get 43.08869 centimeters. If we want to round that to 3 significant figures, it'd be 38.1 centimeters. Okay? And the last dimension I need to get for this problem is the width. And we know the width from our formula here, which came from the constraints, is right here. So this is 20,000 divided by h squared. So we're going to substitute in here. And again, I'm going to show that I'm substituting in my unrounded value by putting an ellipse. And that's squared. Don't forget that squared. It's so easy to forget those types of things with these problems. What we get here is 43.0887014 centimeters. And again, rounding to 3 sig figs, 43.1 centimeters. And you might notice that's the same width and length. So really what we have here, and I kind of cheated a little bit and made my box look a little bit like that anyways, but the length and the width are the same. It's a square-based prism. And that shouldn't be too surprising because some of the basic optimization you probably would have already seen in math was the benefits of the square, of minimizing perimeter and maximizing area. So it shouldn't be shocking that we get a square-based piece coming out of this problem. Okay? So again, parts that I'd be looking for to mark this, I'd be looking for some type of labeled graph. I should have actually put my axis labels. I'd be looking then to see the work in simplifying down a revised objective. Again, the graph from the graphing calculator with the point labeled, and then the calculations and perhaps an optimization statement. Again, following the lead of what the question's asking, and that's key. Okay? Other questions or other variations you can sometimes have is if there was a cost. Maybe the sides cost something different than the bottom to create, or maybe each side is a different price because it's made of a different material or something like that. And then what we have to put is I have to insert the cost values in front of each term. And then you could generate a minimized cost instead of a minimized surface area. And those dimensions might change depending if the costs were the same for all surfaces, it wouldn't change. If the costs were different for the surfaces, then you'd expect that the dimensions would change appropriately. If you'd like to see an expansion of this question where I put some costs in there and we play with that, leave a comment in the comment section and I'll look at trying to make that video before too long. So I would encourage you to, as you revise your questions or you look over your test, make sure you've added things like arrowheads, things that in the moment I had neglected to do. We have an asymptote, so we should probably have an asymptote line along here saying that that's the x equals 0 line. Again, if the graph has an asymptote, you should probably include it. Many times a question like this might only ask for the positive quadrant because you can't have negative dimensions for this type of problem. It doesn't make any sense. Okay? And again, always defer to what your teacher has shown you in terms of examples or what they've set up as standards in the class, for sure. Hopefully you found this example helpful. Thank you very much for listening and watching. Consider liking and subscribing.